So in this video we're going to look at examples of the Mobius inversion formula. By examples, what I mean here is we're going to look at particular classes of post sets and what the Mobius inversion formula tells you in those cases. First, we'll look at our favorite post set, the natural numbers, under the usual ordering of strict inequality. Here it's worth pointing out that a function from the natural numbers to the complex numbers is usually known in calculus courses as a sequence. So here the statements can be interpreted as sequences. So let an and bn be sequences. So this is the role of f, this is the role of g. And this is our partial order. So an is the summation over all I less than or equal to n of bi. So that's one part of the Mobius inversion formula, if and only if. Bn is the summation of all I less than or equal to n, mu of in ai. This is just restating the Mobius inversion formula in the context of this post set. However, we've computed these values before. They're 1 when I is equal to n, and they're negative 1 when I is 1 less than n, so n minus 1, and otherwise they're 0. So this summation actually has two terms. And so here we're saying an is this summation, if and only if bn is this difference. Now I'll state it in the way we actually see it in Calc 2. So you've actually seen this in Calc 2 before. What happens when you're talking about a sum of a sequence from I goes from 0 up to n? You're talking about partial sums. So I'm going to replace b with a and a with s here. The thing on the left-hand side is a partial sum from Calc 2. So one of the corollaries is that if Sn is a partial sum from Calc 2, then the nth term can be found by taking the nth partial sum and subtracting off from it the previous. Admittedly, that formula is not as useful, but when I teach Calc 2, I emphasize that if you're actually computing these partial sums by hand, it tells you that the way to compute the nth partial sum is not to actually sum the first n values, is to, if you're doing a running total, you just take the previous number you computed and you just add one term onto it. And so if you're doing a bunch of partial sums, if you're computing S1 through S52, this goes a lot quicker. Corollary 2 is the other, also pops up in Calc 2. It's this opposite direction. Suppose you have bn is equal to an minus 1. Then the summation of these i's has to be a sub n. Although more accurately, it turns out it's a sub n minus a0 if you actually do the calculations correctly. And you usually see this in Calc 2 because when you see it that way, you're seeing, right, let's see if I can do the calculation correctly. So when we do it in Calc 2, we usually write it out this way, that this partial sum looks like this by the definition here. And then usually you do this creative canceling. You see the A1 crosses off with the A1, the A2 crosses off with the A2, and so on and so forth. And by looking at an example, you see that the only terms that are remaining are an and negative a0. And so you often see this example when you're looking at saying, summing the series n goes from 0 to infinity of something like 1 over n minus 1 over n minus 1. Let's put plus 1 and n. So you usually see these examples, and it's because there's this cancellation property. You get a formula for the nth partial sum this way, and then you compute the limit as n goes to infinity. And that tells you the value of this infinite sum. And so these are two types of things you usually see in Calc 2, and they both fall out from the Mobius inversion formula for free without doing the picture proofs. In fact, actually in some circles, these are called the fundamental theorem of finite difference calculus. I'll explain why in a moment. The idea is that you look at this operation as being sort of a discrete analog of the derivative, and this operation is being a discrete analog of the integral. And if you do that, this theorem turns out to be saying that one function is the integral of another, yeah, I'll do it on the next slide. So here's the idea. We define the discrete derivative, or the backward difference operator, to be f of n minus f of n minus 1. Note this is the slope of a certain secant line in calculus, so the only point is you're just setting h equal to 1 instead of 0. So if you take the definition of the derivative from calculus and set h equal to 1, this is what you get. The discrete analog of the integral is this summation function. The summation of f of n is the summation I goes from 0 up to n, f of I. This is actually a discrete analog of the integral, where you choose to integrate from 0 to n, and every rectangle has width 1, and you're computing a left Riemann sum. And so these two actually do pop up in calculus, we're just not taking limits. Then, with this notation, our Mobius inversion formula looks like this. F is the derivative of g if and only if g is the integral of f, which is exactly like the statement from calculus. And in fact, you actually get that the derivative of the integral is just the original function, and the integral of the derivative is just the function evaluated at the limits of integration, and take the difference. So you get this sort of discrete analog of calculus. In fact, things get a little bit crazier. If you define delta to the n to be delta of delta to the n minus 1, then it's actually a theorem that I'm not going to prove. We'll look at special cases of this, that if sequence is equal to its discrete Taylor series, where this is the definition of the discrete Taylor series we take, this corresponds to the kth power of the derivative, evaluated at 0. Only instead of looking at x to the k over k factorial, it turns out the correct answer is to use the binomial coefficients instead. Surprisingly enough, as we'll see, they form a powerful basis with respect to this notion of derivative. And so, in Calc 1, it's possible for a function to not converge to its Taylor series, but for sequences, as a function, the sequence is always equal to its discrete Taylor series, which is kind of surprising. In particular, this gives you a nice definition of a polynomial. A polynomial is one where this series is finite, which means eventually this delta operator is 0. In fact, you can do a lot of stuff from calculus. Let's define a sequence to be polynomial if a high enough derivative vanishes. So this is the sequences for some k. And this matches our definition. The definition in calculus of a polynomial is one such that the higher derivative is eventually 0, namely 1 beyond the degree. And the same idea happens here as well. We say the degree is the minimum such k, so that this condition holds. Subtract 1. And an example of a polynomial sequence, besides the obvious power sequences, is defining an to be n choose k. You can see that delta of an is n choose k minus n minus 1 choose k, which by the Pascal relation is n minus 1 choose k minus 1. Look, the degree went down by 1. If we're assuming this has degree k. You can prove this by induction on k, by assuming that this is degree k minus 1. And when we do this operation, we get something of degree k minus 1. And so by induction, I get the 0 sequence, where the base case is not that hard. And so the main punchline of all this is that actually every polynomial sequence has a formula in terms of the basis of binomial coefficients. And we know this must be true because the binomial coefficients each have degree k as k ranges, and so they actually form a basis for the vector space of polynomials of a given degree. But you can actually determine it. So given a polynomial, if you actually want its coefficients in terms of the binomial coefficient basis, that should be an x actually. K goes from 0 up to whatever the degree of p is. Then all you need to do is compute these discrete difference operators for this polynomial and then evaluate at 0. And so you actually get this formula. And so I'll do an example in a moment. But this is actually kind of cool. And this actually goes back to algebra. Some of you have probably seen this before if you go back far enough in the recesses of your memory. So to get at it, here's the idea. Suppose your sequence starts with these values, and you want to see if it's a polynomial. The one thing you learn how to do is to take differences. So 10 minus 11 is -1, 13 minus 10 is 3, 20 minus 13 is 7, and 31 minus 20 is 11. We see here that we don't actually know the degree of the polynomial yet, and we don't know if it's a polynomial sequence yet. But if we keep doing this, 3 minus -1 is 4, 7 minus 3 is 4, 11 minus 7 is 4. And so now we see that we get a constant, and so if you go one step further, you get the 0 sequence. And so I remember learning this in Algebra 2, that if you do something like this, you see that you must have a quadratic. And so in Algebra 2, once you have a quadratic, then you have to solve for the unknown coefficients. But here it's worth pointing out that you could actually write down the quadratic equation or formula for this quadratic using binomial coefficients. How so? Because if you look down this diagonal here, what you're getting is the zeroth difference operator, or p of 0 in this case. What you're getting here is the first difference operator applied to 0. This is the second difference operator applied to 0. And this is the third difference operator applied to 0. And so by my formula, I have p of 0, which is 11, plus delta of p of 1, which is -1, times my binomial coefficient, x choose 1, plus my next coefficient is 4, times the binomial coefficient, x choose 2. And so if you use this approach, if you're given the sequence of first so many values of this polynomial, you can actually compute a formula for the polynomial immediately. And then using your formulas for binomial coefficients, you can actually solve for it in terms of powers the way we're used to seeing it. But you can also get the information right here. And so naturally, this has gone far afield from Mobius inversion. We see how this idea of finite differences actually leads to stuff that looks a lot like calculus, down to even simpler ways to find formulas for polynomials. So all I knew to find this was just the value of the polynomial. All I needed was up to here. So knowing the first 4 values of the polynomial at the first 4 non-negative integers was enough to give me a formula. It's also nice because you sort of see this important polynomial playing the same role that the power functions do in Calc 1. In fact, actually the x to the fallen k play the same role. If you take the forward difference operator of x fallen k, you will actually get k times x to the fallen k minus 1. So the falling factorial functions play the same role, and the differential operator has the same power rules in Calc 1. And so you get a lot of deep analogies here, and a lot of it falls out just from Mobius inversion. Now finally, we move on to our next example of a poset. Let P be the power set of X, so it's the set of all subsets of X, ordered by inclusion. Let F and G be 2 functions from the power set to the complex numbers. Then the Mobius inversion formula says f of S is equal to the summation over all t, where t is a set containing S and containing X, G of t. So this equality holds for all subsets of X. If and only if this corresponding function holds, G of S is equal to this summation, U of ST, F of t. But we've already computed this Mobius function. It's just -1 to the size of t take away S. And what do we get? This is one of the formulas I claim as the inclusion-exclusion principle. So the principle of inclusion-exclusion is just a special case of Mobius inversion. So this is a vast generalization of the principle of inclusion-exclusion for accounting problems that don't involve subsets. As we already saw, if you switch post sets to the natural numbers, you actually get a lot of interesting calculus analogs. And so it's good to work with multiple post sets. As a third example, let P be the divisor lattice. So this is as I said, it's the natural numbers, but the partial order is the divisibility relation. Now I'm given two functions, f and d, from the divisor post set to C. So these are actually just sequences. We're requiring by Mobius inversion for f of n to be the summation over d less than or equal to n, g of d. But what does that mean in this post set? It means summing over all divisors of n, g of the divisor. So this equality is true if and only if, by the Mobius inversion formula, g of n can be computed by summing over all divisors of n, mu of dn, f of d. Again, of course, we've computed this before. Mu of dn is by definition mu of n over d, where this is the classical Mobius function I've mentioned before. Mu of d is -1 to the k when d is a product of k distinct primes, and otherwise it's 0. And so this is the classical Mobius inversion formula, where the Mobius inversion gets its name. It pops up when you're studying counting problems involving divisibility. And I'll give two examples of applications of this Mobius inversion formula. One involving an example we already studied using principle of inclusion-exclusion, and one new example. So the old example we did was the Euler-Phi function. So I need to prove this claim. N is equal to the sum over all d dividing n phi of d, where phi is the Euler function. If that were true, then by Mobius inversion, phi of n is the summation over d dividing n, mu of n over d, times d, because that's this sequence here. And what can you get from that? Well, this order of summation goes over all divisors, so n over d is also a divisor, so I can re-index summation, u of d times n over d here. So I'm just swapping the roles of d and n over d. I can do that. You can pull out this common factor of n, and then remember that this term is 0 unless d is a product of k distinct primes, whose product divides n. In that case, it's -1 to the k. In that case, d is itself the product of p1 through pk. But of course, at this point, you see that you should be able to simplify as follows. Namely, you can rewrite that product as a product of 1 over pi and bring the negatives in, so it's -1 over pi. And you're summing over all these divisors. And we did this example when we did principle of inclusion and exclusion, and we saw that you could get from this summation to this product by doing a generalized multinomial formula. The point is, how do you determine a term in this product? Well, you're picking a subset of these prime divisors and picking the right-hand term in those divisors. That corresponds to picking k distinct prime divisors and multiplying them together, multiplying -1 over pi for each of them. And the other terms, you're taking the left factor, which is 1, so it doesn't pop up in this formula. And so we've derived our formula for the Euler-Phi function using just Mobius inversion. It's debatable which approach is nicer. And so, again, since it doesn't matter if you're summing over the divisors or their quotients, I'm actually going to look at this summation instead. Phi of n over d, where d is dividing n. And what is phi of n over d? Well, it's those integers less than n over d that are coprime to n over d. So their GCD of I and n over d is 1. So summing each of those exactly once. However, if I multiply through by d here, I have d times I is less than or equal to n, and the GCD of d times I and n has to be equal to d. But then I see that I can reindex the summation by setting j equal to d times I, and seeing that the GCD of j and n must be d. Why is this allowed to get away with? Well, because if the GCD of j and n is d, in particular d is a divisor of j, and so j must be able to be written as d times I for some integer I. So even though this looks like a loss of generality, it's not. But now I'm just summing over numbers less than n based on their GCD. And so every number appears, and so this is actually n. So that proves this part. And then Mobius inversion gives us our other more popular formula for the Euler-Phi function. So I give one more application of Mobius inversion for the divisor lattice, and this application involves a lot of abstract algebra. So we're going to let f sub q be the finite field with exactly q elements. It's a theorem in abstract algebra that there's a unique up to isomorphism such field whenever q is a power of a prime. So if you haven't taken enough abstract algebra, just assume this is z mod p z, where p is a prime number, because you prove in an undergraduate modern algebra course that that is in fact a field. So one of the facts from algebra we're going to assume without proof is that every irreducible polynomial of degree n over this field divides this polynomial. In other words, that you can actually factor this polynomial, x to the q to the n minus x, as a product over all such irreducibles. And that's a deep theorem in modern algebra. And we're going to use that in a moment. And so we're going to let u sub d be the number of irreducible polynomials of degree d over this finite field. And that's the thing we want to count. And yet it turns out it's hard to count it. What we can do, though, is we can prove this identity, that q to the n is equal to the summation over all divisors of n, d times u sub d. Why? Because each irreducible polynomial of degree d gives d distinct roots, has d distinct roots by theorems of algebra. There's no multiplicity, they're all distinct. And since f of x appears in this product, these d roots are roots of this polynomial as well. And so in particular, each polynomial gives you d roots. You sum over all the possible roots. Divisors, you're getting all the possible roots. How many roots are there to this equation? Well, because this polynomial has degree q to the n, there must be at most q to the n distinct roots. Using derivatives, you can actually prove there are exactly q to the n distinct roots. There's no multiplicity at all. And so it turns out this equation is true. This is just counting roots of a polynomial two different ways. So it's a very abstract version of the double counting argument. And what that means is by Mobius inversion, n times un, that's the sequence over here, is the summation over all d dividing n, the Mobius function of n over d times q to the d. So just divide through by n, and you now have a closed formula for the number of irreducible polynomials of a given degree over a given finite field. In particular, you can prove this number is always positive, so irreducible polynomials actually exist. However, admittedly, this application requires knowing a lot of stuff in modern algebra. I remember once in graduate school having to take a qualifying exam in algebra where this exact problem popped up on my 2-hour test. And so it was nice to remember the proof. However, this gives you a flavor of how Mobius inversion pops up in real life. Oftentimes it pops up in other areas of mathematics where you're trying to solve some counting problem, and end up realizing you're working with some partial order. And then this allows you to use Mobius inversion to solve your problem, provided you can compute this Mobius function. And so this is the motivation for why we study partially ordered sets and Mobius inversion formula, because it allows us to solve harder counting problems.